Hello, everyone. Mr. Minix, my name, math is my game. Today, in Algebra 2, we're looking at Chapter 2, Section 7. The title is Graphing Absolute Value Functions. Graphing Absolute Value Functions. So if I were taking notes, I might have some graph paper available. If you're in class and you'd like to grab a sheet or two, there's plenty on the side table over there. So we're going to be graphing absolute value functions. Before we get into that, we probably ought to recap 2.6 just a little bit. In 2.6, we talked about three kinds of transformations. Three kinds of transformations. And this is going to be a 72-second review of 2.6. Transformations, we said there were three kinds. We said there were translations. What a translation is simply is when the graph is like Madagascar and you say, I like to move it, and you just move the graph around. Okay, so whatever the function looks like, we're just moving it to the right, to the left, up or down. And that's a translation, and that happens when we take f of x plus or minus, or f of x plus k, or we take f of x plus k like that. Okay. So that happens whenever we're adding some kind of number to the end of the function or inside some parentheses to the function. The other kind of transformation we had was a reflection, and that's where we take the graph and we flip it over, usually the x-axis. Okay, so that's where you just kind of put a negative sign in front of the function. And then the third kind of transformation, I'm pretty sure we said was a either a stretch, a vertical stretch, or a vertical compression, And they both happen by doing the same thing. What we do here is we multiply the function by some multiplying factor, k times f of x. In either situation, we multiply the function by some constant k. Okay. Does anybody remember what k is if we're stretching the function out? What k is equal to? How big of a number? With respect to the number 1, how big is k if we're stretching something out? Anybody? Bueller. If we're making something bigger, how much bigger than 1? Well, anyway, the point is it's bigger than 1 if we're stretching it out. Okay, if we're stretching something out, k is bigger than 1. If we're compressing something, k is between 0 and 1. Okay, so there's going to be an essay question on the Unit 1 test that deals with transformations, so be ready for that. So I guess we probably ought to get right into graphing an absolute value function. So we talked about parent functions. So here's the parent function again, the parent absolute value function. We really need to be able to graph this thing with one hand tied behind our back, with our blindfolded, that kind of thing. We really ought to be able to graph this right away. And to graph it, I'm going to start with a table of values. Okay. So I'm going to randomly pick some x values like 0 and -1 and +1 and 2 and -2 and 3 and -3. And to find my y value, it's of course going to be the absolute value of x. So what's the absolute value of 0? The absolute value of 0 is 0. Good. And what's the absolute value of -1? 1. And the absolute value of 1 is 1. And the absolute value of 2 is 2. And the absolute value of -2 is 2. And I think we get the idea now, right? So plotting these points, then we can see that this graph goes through the point 0, 0, 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, negative 3, 3. And I think by that point, we kind of get the idea what this graph's going to look like, huh? So if I'm sketching this by hand, I'm going to go ahead and draw something like that and something like that. And I'm going to highlight some of the finer points of the graphs here. When you graph these on paper, I do expect you to include those things, those little arrows. That doesn't mean that the graph doesn't stop. It goes on for a long time. It goes on infinitely, in fact. So I think what we ought to talk about then with respect to this graph is its domain, its range, maybe a couple other finer points on the graph. So let's think about the domain. The domain is all the x values that the graph could take on. And we can see that we chose 0, we chose negative 1, we chose positive 1. Are there any x values that we couldn't pick? Are there any x values we couldn't pick? Kind of a tough question to answer. I know we're just getting into this. Anyway, the point here is there's no limit as to what we could pick for x values. Anything along the x-axis is fair game. So what we'll say about the domain is the domain goes from negative infinity to infinity. The domain is all the x's that are between negative infinity and positive infinity. Okay? The domain is all real numbers. There's no restriction whatsoever on the domain of this. Okay, so the domain is all real numbers. Goes from negative infinity to positive infinity. Now, when we're talking about the range of this function, the range is a little bit different. The range is a little bit different. The range, if we look at those arrows are going up forever, but those arrows don't go down unlimited. So, anybody think they have an idea what the range is on this? What do we got? In between the lines. In between what lines? In between the blue lines? Well, in between the blue lines. Basically, wherever the blue goes, all those y values where the blue could go. So let's think about where the blue could go. What's the lowest it could go to? It could go to 0, right? So the range goes from 0 all the way up to the maximum that this could go to, which is infinity. Nice, good. Now we're cooking. So the range goes from 0 to infinity. We would say that all the y values are less than infinity and greater than or equal to 0. Okay? So the range is all the values of y greater than or equal to 0. How are we feeling? I know it's a Monday morning. If you're watching this back on Tuesday, well, then it's Tuesday for you. So there's a point on the graph. I'll put a star on it right there. You need to know the name of that point. The name of that point is Jackson. No, it's not Jackson. Maybe it's Neo. No, it's not Neo. Maybe it's Samantha. No, it's not Samantha. What's the name of that point? The highest or lowest point on the graph, yeah. It is the origin, but with respect to the graph and the fact that it's the lowest point on the graph, we call it the vertex. Okay, so we call that the vertex. And the vertex of this graph occurs at the origin. And I think that's about it. How are we feeling about these so far? Pretty good? So, to recap this business about transformations, remember, if we translate a graph, the graph stays the same shape, stays the same size, the orientation of it as far as opening up or down or sideways, the orientation stays the same. We just move it around a little bit. So what we're going to do now is we're going to try some translations on some graphs. Okay, so we'll go ahead and graph a few of these. And in the exercises tonight, you'll be doing the exact same thing. Example 1, graph y equals the absolute value of x plus 2. Graph y equals the absolute value of x plus 2. Now what I'm going to do is I'm going to graph the parent function, which we knew what it looked like. I went through the origin, 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, negative 3, 3. I'm going to graph the parent function. And it's nice because I have the smart board. I could kind of cheat a little bit. I could clone this thing. I could change colors of it. I'm going to make this one red. And when we have x plus 2, inside the parentheses, that's either going to translate this graph up 2 units, down 2 units, right 2 units, or left 2 units. Maybe we better go and check the notes from last week. Maybe we better go and check the notes from last week. I have them stored on my handy flash drive. They are on Math Excel for School also. So last week, 2.6 notes. Let's see. Vertical translations are up and down. It's when we add something to the end. So x squared plus 6, x squared minus 8. But we're dealing with absolute value functions. That's okay. Horizontal translations left and right when we add or subtract something inside the parentheses. If you can read my writing there, if we add some number in the parentheses, it translates the graph to the left. If we subtract, it translates the graph to the right. So in this case, that x plus 2, is it going to translate the graph 2 units up, 2 units down, 2 units right, or 2 units left? 2 units to the left. You'd think to the right, but it's actually 2 units to the left. Okay? It's actually 2 units to the left. And that's it. Say the graph is the same size, it's the same shape. It's the parent function. It's just translated 2 units to the left, to the left. And what's interesting is what changes from the parent function. The domain of this graph is still the same. The domain is negative infinity to positive infinity. That's never going to change for most polynomials, for all polynomials. The range is still the same. The range goes from 0 to infinity. What changes is the location of the vertex. The vertex in this case is at negative 2, comma 0. The vertex is at negative 2, comma 0. So if I'm taking notes, if I'm making notes on my notebook, notes to myself, I'm going to have this thought bubble. Let's see if I can find a thought bubble. I know there's one in here. Here we go. So my thought bubble to myself is this. My thought bubble to myself is, self, this is kind of weird. Whenever the graph translates to the right or to the left, what's happening is something's being added inside the parentheses or inside the grouping symbols. Inside the absolute value moves the graph to the right or to the left. And if we add something, it moves it to the left. And on the other hand, if we subtract something, it's going to translate it then the opposite way, to the right. So if I have a thought bubble, I'm going to maybe think that to myself. Make a note of that, because I'll be honest with you, this is the one that people mess up all the time. Translating up and down, everybody gets it. But translating right and left, these are the ones that people mess up all the time. Wasn't there a country song about that? Dogs do it, or kids do it all the time, or something? I don't know. It's probably too old by now. So maybe we should try another one. Maybe we should try another one. So this one we've got y equals the absolute value of x with a minus 3 tacked on the end. With a minus 3 tacked on the end. So again, I'm going to graph my parent function. My parent function goes to the origin, 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, negative 3, 3. So there's my parent function. And I know what you're thinking. You're thinking, well, I can't do this on my notebook. Yeah, you're right. I'm sorry. This is kind of cheating for me. But that minus 3 at the end of it, that minus 3 at the end, what is that going to do to our graph? It's going to move it down 3 units, right? So anytime we have something being added or subtracted to the end, it's simply going to translate the graph down 3 units, and that's it. That's it. Let's think about our domain and our range on this one. The domain is still all real numbers. The range goes from the lowest point of the graph. Now our vertex here is 0, -3. So the range is actually going to go from -3 up to infinity on this one. Okay. How are we feeling about this so far? All right. Now, I don't know if anybody in here does skateboarding. I tried skateboarding back in the day. True story, my neighbors, I don't know what they did for a living, but they had about 75 sheets of plywood in a big storage dumpster back in the middle of the woods. Now, I lived in the country and my road was chip and sealed. Can anybody relate to a chip and sealed road? It's kind of hard to skateboard on a chip and sealed road. But I had this nice big hill for my motocross track. So I went and got all this plywood and lined it up end to end to end of my field, and I had a really nice quarter pipe. It was pretty fun. But anyway, when you skate, you do one trick and you feel pretty okay about it after you fall 2 or 3 times on your face and skin your knees and get the splinters out. And then you learn another new trick, and you feel pretty good about that. And then you try to link the two together, huh? Let's see if we can link the two together. Let's see if we can link the two of these together now. Example 3. Example 3, we're going to graph y equals the absolute value of x minus 4 minus 7. All right. I know this is really making you mad, so I'm not gonna clone that this time. Okay, but let's imagine, let's picture where this new graph's gonna be with respect to the old graph. Do you hear that? Listen. Do you hear it? Do you hear that? Do you hear that? Hold on a minute. I think this is trying to say something to us. I think x minus 4 is trying to tell us something. What's the x minus 4 trying to tell us? That the graph's going to be translated to the, you would think to the left, but it's to the right. How much? 4 units. So the x minus 4 tells us the graph's translated to the right 4 units. So in other words, this thing's going to be over 4 units to the, oh, better not do that. It's going to be translated 4 units to the right. And then what about that minus 7? What's that telling us? It's going to go translate down 7, right? So down 7. So when we sketch the parent function, we kind of start at the vertex, right? The lowest point. So let's do that. Let's start at the vertex. So from the vertex, we'll be going right 4 and down 7. So right 4, 1, 2, 3, 4, and then down 7. There's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's 7. So that's kind of like my starting point right there. Remember, this is the exact same size and the exact same shape as the parent function. So we know the parent function from the vertex. We go over 1 and up 1, and then we do this, and then we do this, and then we do that. And then we can say that our domain is still negative infinity to positive infinity. That's not going to change on any of these. And then our range goes from the lowest point up. And the lowest point is where my vertex is. My vertex is at 0, -7, so it goes from -7 to infinity is the domain, or is the range, I'm sorry. How do we feel about that? Would we be able to graph one of those on our own? On a piece of paper without a graphing calculator? Got him? Piece of cake? Okay. So now that we learned to link 2 tricks together on our skateboard, we're going to learn a new trick. And we're not going to link it together with these other ones yet, but we will before it's all said and done. So example 4, time to learn a new trick. This time we're going to graph y equals negative the absolute value of x. Okay. Y equals negative the absolute value of x. So if you go back and you look at the translations, or transformations, I should say, this is a reflection, right? Put a negative in front of the grouping symbols, and this is a reflection. So in a sense, it flips it over. If you think about a table of values, all the y values that used to be positive are now going to be negative. So any idea what this one's going to look like? We'll still start at 0, 0. That's where my vertex is still going to be. But where's my next point going to be? I'm seeing people kind of point down. Yeah, we're going to go over 1 unit and down 1 unit. And over another unit and down 1, and over again and down 1. And so basically it's going to look just like the parent function, except it's going to be flipped over. It's going to be upside down. It's going to be reflected about or around or across the x-axis. Okay? So you mean to tell me if I were to sketch this graph, make this one blue like we were using for that parent function, if I were to take this thing and flip it, then it would be the same thing as a parent function? Yeah. Same thing as a parent function, just flipped over the x-axis. We doing all right with this? Now let's see how our domain and our range changes. Our domain is still going to be negative infinity to infinity. Our range is going to change. I'm going to put an asterisk here. Our range is going to change. Remember, these graphs had been opening upward to the sky. And our range went all the way up to infinity. I'm using this interval notation, and in this interval notation, what you got to realize is this number on the right here, that's the maximum that the thing could take on. So when I use this interval notation, the maximum value that this graph can take on is 0 on the y-axis, or on the y end of things. And the minimum number is negative infinity because this graph opens downward. Okay, so the range is a little bit different on a reflection. The range doesn't go up to infinity, it goes down to infinity. Okay. All right, so if I'm making a thought bubble to myself, note to self, the range changes with reflections. Be careful on that. Any questions about this? Comments? Anybody like to give a shout out to anybody? If somebody in YouTube land is watching this video. Okay. Well, let's try to link a couple tricks together now. Example 5. Let's try to graph y equals 2 minus the absolute value of x plus 1, like that. Woo! Now, this is not in the form that we've been seeing it in. This is not in a nice form. So let's first of all write this so that it's in a form that's similar to what we've been working with. What's that going to look like? It's still going to be y equals, but what's going to be first? Let me kind of highlight each term so that we understand what's going on here, because this is a little bit different. This 2 is a term, and then there's a coefficient. This -1 is kind of the coefficient, so that really makes that thing a term. So what's this going to look like in the form that we've been dealing with? Y equals how about negative the absolute value of x plus 1? Now, what are we going to do with that 2? What are we going to do with the 2? Yeah. It's going to be added at the end, so it's going to be plus 2 at the end, right? Does that make sense? Because these ones really trick people up. People get kind of tricked up. I don't know, they drop the ball on these ones. Okay, so let's think about what each part tells us. This x plus 1 tells us that the graph is going to do what? Translates to the left 1 unit, so the graph's going to be left 1. The plus 2 tells us that the graph's going to do what? Translate up 2. And then finally, this negative here tells us that the graph is going to do what? It's going to be opening downward. The graph is going to be opening downward, okay? So when we go to graph something like this, we need to take all those things into account. We need to take all those things into account. So I like to locate my vertex first. So my vertex is not going to be at 0, 0. We said it's going to be, not only is it going to be left 1, but it's also going to be up 2. So that's the location of my vertex. So my vertex in this particular graph is going to be at -1, 2. Okay? Feeling all right about that so far? Okay? And then the negative tells us the graph's going to open down, so you got to know that parent function well enough to know that from the vertex you're going to go over 1 and down 1, and then over 1 and down 1 again, and over 1 and down 1 again, and then because of symmetry you can do the same thing on the other side. And so that is what this graph's going to look like. Domain is still -infinity to infinity. The range goes all the way down to -infinity, and it goes as high, the range goes as high as 2. Okay. So hopefully everybody's kind of feeling okay about graphing these so far. So let's see. What's a trick on a skateboard? Is an ollie a trick? So an ollie's one trick. So we learned how to ollie. Another trick is just riding switch foot, right? Like if you ride with I normally ride with my left foot forward. So if I rode with my right foot forward, that's switch for me. Even though I think when you're left foot forward, don't they call that goofy foot? I don't know. So anyway, so we learned how to do an ollie. We learned how to ride switch. Maybe we want to do a manual. Isn't that where you go up on one axle, on like just on the back? So if you think about what we got going here, we can ride switch foot. We can ride. We learned how to do an ollie. Did I say an ollie already? So we can do an ollie, a switch foot, and a manual, and we can link them all together. And that's pretty good. If you were playing a video game, that'd get you quite a few points. Well, now we need to send this over the top. We need to send this over the top. We need to learn a new trick, and then we'll tie it all together. Example 6. Example 6, let's graph y equals 4 times the absolute value of x. What I'd like to do here is put a table of values in for the parent function, and then also put a table of values in for the function that we're going to be graphing. The parent function goes through 0, 0, and 1, 1, and 2, 2, and -1, 1, and -2, 2. This function says, you know what we're going to be doing to the y values is we're going to be multiplying all of them. And it's kind of interesting that this particular column right here, those are really our y values. What we're going to be doing is multiplying all those by 4. 0 times 4, or 4 times 0, I should say. 4 times 0 is still 0. 4 times 1, what's that going to give us? 4 times 1 is going to be 4, and 4 times 2 is going to be 8. Good. Okay. So putting this into play then, our parent function goes through 0, 0, 1, 1, and I'm going to go ahead and stop there. This other function is still going to go through 0, 0, but then it's going to go through 1, 4. Make sure I go up high enough. This one goes through 1, 4, okay? And then the parent function then went through 2, 2. The parent function then went through 2, 2. But this function goes through the point 2, 8. This is going to go through 2, 8. So 2, 8, 2, 8. Okay, so the parent function, from what we saw, kind of looks like this. If we want to talk about slope, we could think of it as having a slope of 1, even though the slope's positive sometimes and negative other times. But this other function, it's really steep, and it has a slope. If you want to think of a slope of either 4 or negative 4, depending on how you look at it. But otherwise, it's still opening up. Still has a vertex at the origin. So same vertex. The domain still negative infinity to infinity. The range still from 0 to infinity. And it looks like the graph's narrow, and it looks like it's never going to get to infinity on the x-axis, but it's going to get to infinity on the y-axis faster, but some infinities are bigger than others, and that's okay. How do we feel about that one? Okay. So that is a vertical stretch by a factor of 4. We got 2 more. Example 7. Y equals negative 1/2 times the absolute value of x. This negative tells me what? The graph's going to open upside down. Nice. So it's a reflection. So the graph's going to be opening downward. Okay. So hopefully now we kind of get an idea of what that 1/2 is going to tell us. What's the 1/2 going to tell us? That the graph is going to be when we had a k value of 4, the graph was stretched. When we have a k value of 1/2, the graph is going to be, starts with a C. That's a compression. Good. It's going to be a compression. Okay. So let's see what's going to happen. Our vertex is still going to be the same. Our vertex is still going to be 0, 0. This graph is opening upside down, and all my y values get multiplied or cut in half. So I guess what I'm saying is this next point, be careful. The next point on the parent function would be over 1 and down 1, but we're not graphing the parent function. We're not graphing the parent function. This half right here says, all those y values get cut in half. So anytime you're changing on that y-axis, you're going to move half as much. So instead of going down a full 1 unit, we're going to go down half that much. So we're actually going to be going through this point right here and this point right here. Okay. The parent function says if we go over 1, or over 2, we go up 2, or a reflection would say if we go over 2, we go down 2. But keep in mind, that 1/2 says we're going to be going up or down half as much. So instead of going down 2 units when we go over 2, we're going to go down how much? Somebody said it? 1. Good. Okay. So instead of going over 2 and down 2, we're going over 2 and down 1. Do we get the idea there? Okay. So the graph is essentially flattened out. Okay. So the domain is still negative infinity to infinity. The range, remember our reflection, the range changes. The range goes down to negative infinity, and the range goes as high as 0 in this case. Okay. So we learned how to ollie. We learned how to ride switch foot. We learned how to do a manual. And I guess this is a kick flip. Can we put them all together? Let's see if we can. Here we go. The ultimate, the last one, example 8, graph y equals y equals 4 minus 2 times the absolute value of x plus 3. Now this isn't in a very nice form. Again, we want to switch the form. We want to put the absolute value stuff out front. Remember, we've got a couple different terms here, and this 4 is kind of like that thing that's really being added to the end of the function, being tacked on to the end of the function. This whole thing is one term, so really we probably ought to rewrite those terms so that it's in a form we recognize. So we're going to rewrite this as y equals what? Yeah. Perfect. -2, absolute value of x plus 3, and then plus a 4 on the end. Okay? So once we get it in that form that we recognize, now we'll say, okay, so this x plus 3, I think that that's going to make the graph go to the right, but the right and left is the opposite of what I think. So that plus 3 actually makes the graph go to the left 3, left 3. The plus 4 does what with the graph? Takes it up 4. The negative does what to the graph? Makes the graph so it's going to open down. And then the 2 finally, what's that 2 do? The 2's going to, isn't that going to stretch it out? Okay, the 2's going to stretch it out. So let's see if we can put this all together. Notice we haven't used a graphing calculator at all the whole time. And we don't need to, because we got this. We got this. We got this. Entire page. Here we go. We'll lock that in place. So we said that the vertex is going to be left 3 units. So left 1, 2, 3, and then up 4. 1, 2, 3, 4. So that's where our vertex is going to be. Our vertex is going to be at -3, 4. We said the graph's going to open downward, and it's going to be stretched by a factor of 2. So when we go over 1, normally we would go down 1, but we're stretching that out. Instead of going over 1 and down just 1, we're going to go over 1 and down 2 units. Okay? And by symmetry, we can go over 1 the other way and down 2 units. With the next point, normally when we go over 2, we go down 2, but we're doubling that 2. So when we go over 2, we're actually going to go down not 2, but 4. Okay, so we're going to go over 2 and down 4 like that. And once we get a couple of those, I think now we got an idea. I didn't make it through that line very good, but you get the idea here. Okay, so my domain is, again, all real numbers. My range goes from -infinity clear up to 4. And that's the way. I like it. I'm going to give a shout out to the future Mr. Minnick. I'm going to give a shout out to Hayden Nichols. I'm going to give a shout out to Sarah Koenig. She's probably got about 7 questions she'd like to ask right about now. And I'm not picking on Sarah. I'm just saying Sarah is a good student like that. I'm going to give a shout out to Cole Dean. I'm going to give a shout out to Zach Ober. I'm going to give a shout out to Alicia. And I'm going to give a shout out to Seth and Travis Gibson. Any questions, comments, concerns? If not, it's been real. It's been fun. Have a great day. See ya.